Assalamualaikum and a very good day to everyone, especially to our lecturer. So today we are from group A3.4, section 3. We are going to present our Power Engineering Laboratory 3 for AC 3-phase 2-pole synchronous motor, activity 2 MMEA. Okay, so first of all, this is our group members, Hanafi Adli, Iskandar Shah, and Yusof. Okay, so first of all, for introduction, what is synchronous motor? So the most common types of AC motors are the synchronous and induction motors. A synchronous motor differs from the induction motor in that it does not rely on current induction to produce the rotor magnetic field. A synchronous motor is one in which the rotor normally rotates at the same speed as the revolving field in the machine. Therefore, it rotates at a rate log to the line frequency. The principle of operation of a synchronous motor can be understood by considering the stator windings to be connected to a three-phase alternating current supply. Okay, so next for the lab activity. For data collection, star circuit. Okay, so first, for this lab, the objective is first we want to study the basic construction of AC three-phase two-pole synchronous motor. And then we want to study the concept of synchronization and to conduct the variable excitation test on a three-phase two-pole synchronous motor under loaded condition. Okay, so first of all, we need to assemble the motor and set the circuit connection to star. And then as we can see from the table, the load that we will be using is various from 0 Newton meter to 0.8, but the speed is constant at 3000. But as you can see, when the load is 0.8 Newton meter, the values are uneven or zero due to the fact that the motor is completely stalled. Okay, but to conduct the experiment, after we run the motor at 0 Newton meter, and then we will record the reading for voltage, current, power, and power factor based on the meter on the lab. And then gradually we will increase the load from 0 to 0.1, and then 0.2, and until 0.8. And then we will record the reading for the table. Then next, for the DC voltage and current, also we will record from the voltmeter at the lab. And then for horsepower, we will calculate using the formula of horsepower equal to power divided by 746. As we know that 1 horsepower is equal to 746 watt. So we will be using that formula to calculate the horsepower for the star connection. Then next, for the data collection of delta circuit. So same as star circuit, we will assemble the motor and set the circuit connection to delta. And then as you can see from the table also, the load that we will be using is varies from 0 to 0.8 Newton meter, but the speed still remain 3000 RPM. And as you can see, at 0.8 load Newton meter, the value is uneven because due to the factor that the motor is completely stalled, which is the motor reach uh, its maximum to handle the load. And then we will do the same step, which is we will record the voltage, current, power, and power factor for the motor. And then we will start from zero load and gradually increase to 0.1, 0.2, and until 0.8. So next, for the DC voltage and current, also we will record from the voltmeter at the lab. And for the horsepower also, we will calculate using the formula horsepower equal to power over 746. As we know that the horsepower is 1 horsepower equal to 746 watt. Okay, so that's all from me. I will pass to the next presenter. Thank you.
Okay, thank you to my friend Muhammad Iskandar Shah. Then my name is Muhammad Hanafi Adli, and I'll be present for the next slide. Okay, for this task, using proper color codes to complete the equipment arrangement layout shown in figure 4.7 with a star wiring connection. Next. Okay, this is the star wiring connection, which consists the equipment is we got a DC supply, a AC three-phase supply, a multimeter, which is current and voltage meter, analog voltmeter and ammeter, and we got 4 power digital meter, and we also have a motor assembly panel and a motor drive that will drive the motor later. Okay, first of all, from the three-phase supply, we got we need to connect uh, the wire to the 4 power meter, which is the voltage for the current ampere, and the power watt and the power factor. Uh, and then we from the power factor, we need to connect the red and yellow wire to the stator, and from the power factor, um, by using blue and black wire, we connect to the coil and to the neutral. Okay, from the carbon brush, we connect to the digital DC ammeter, and then from the digital uh, ammeter, we connect it to the DC supply. For the um, negative carbon brush, we connect it to the DC supply. Beside that, from the digital DC voltmeter, we need to connect it to the DC supply too. After that, from the DC supply, we need to connect to the DC voltage voltmeter, analog voltmeter, and we need to for from the DC supply, we need to change the value to get the result. Okay, this is for the star connection. Next. Okay. For the next task, by using a proper color code, we need to complete the equipment arrangement layout shown in figure 5.8 with a delta wiring connection. This is the connection with the list of equipment is same to the previous connection. Okay, from the three-phase supply, we need connect to the voltage voltmeter, to the current ammeter, and to the power meter, which watt, and lastly to the power factor. Okay, from the power factor, by using the red wire, we need to connect to the stator, and for the yellow wire, we need to connect it to the stator too. For the blue color, blue wire, we need to connect to the coil. After that, from the positive carbon brush, we need to connect to the digital DC ammeter, and from the digital ammeter, we need to connect it to the DC voltage voltmeter. For the negative carbon brush, by using a black wire, we need to connect it to the DC supply, and from the DC supply, we need to connect it to the DC voltage voltmeter. And from DC supply to by using the red wire, we need uh, connect it to the DC current ammeter to get the value, and by change the value from the DC supply to get the result that we need. Okay, next. Okay, for next task, by using proper color code, um, we need to complete the stator layout shown in figure 4.1, 4.9, which a data wiring connection. Okay, this the coil connection view from drive. As we know, uh, in the coil connection, it's need 4 pair of um, connection, which two of them is a pair uh, connect opposite to them. As example, for connection 2 and 3, a pair of connection 2 and 3 need to be pair or need to be connected to opposite of them, which is the connection of 9 and 8. And same goes to other. For the yellow, we need a connection of 4 of them, which is two pair of 10 and 11 connect to 4 and 5. For red is 1 and 12 connect to the opposite of them, which is 7 and 6. As we know, the red wire is the input of them, which is will be connected to the coil number 6, and the yellow one will be connected to coil number 10, and the blue one will be connected to coil number 2. And from coil number 4, we need to parallel it to the B, which is here. And then for the neutral, we don't need to connect them. So this is the explanation for this task. Okay, that's all from me. Thank you.
All right.
Okay, you guys, thank you.
Okay, thank you, Hanafi. Now I'm
Welcome.
going to answer the question, the plot the graph or calculate horsepower versus log torque. Okay, this first question is calculate horsepower versus log torque. So for the star connection and delta connection, so we get this result based on the table we explained by the Iskandar. So this is our result table. Okay, for the next plot the graph. Okay, we have to plot the graph of SC current, ISC stator, RYB versus log torque. Okay, this is our plot graph. So the first for the star connection and delta connection. So we know that there has some small difference between them. Okay. Okay, the last we have to the plot graph of DC current, IDC armature versus lot torque. Okay, this is our plot graph for the star connection and delta connection. Okay, as you know well, so DC current, IDC armature versus lot torque. For the star connection, we get this graph. And then the data connection we get the straight graph, and then it's increased to the almost 3.5. Okay, the last question, the question given is explain why the shaft horsepower is linearly related to the load torque. So the answer is the horsepower is related to torque since it include the torque into the equation. The power is equal to the amount of work done in certain amount of time. Horsepower is calculated as torque multiplied by revolution per minute (rpm). A motor must create more torque or operate at a higher RPM to produce more power or both. That's all from me. I will give to the next presenter. Thank you.
Okay, thank you, Muhammad Yusof. So for conclusion, in conclusion, The lab work is done to study the construction of an AC three-phase two-pole synchronous motor, which is made up of several pieces including a stator and a rotor, and is powered by a three-phase AC supply. After conducting this lab work, the student was able to understand the concept of synchronization, which is the process of matching the frequency of a generator or other source to a running network. When an AC generator is not running at the same frequency as the network, it will not be able to deliver power to it. And last but not least, the behavior of the synchronous motor was studied when the load torque was added to the motor. As a result, the larger the load torque, the more horsepower is required to rotate the motor. So that's all from our group. Thank you.